All right, Honors Chem, this is Lesson 8, Covalent Bonds. This is the last lesson in the Foundations unit before we move on to the next unit of reactions. So covalent bonds occur when two or more atoms share electrons. Covalent bonds occur primarily between nonmetals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, and chlorine, and the others. Covalent bonds produce combinations of atoms called molecules. And covalent bonds are the bonds that are found in you and other living organisms. So just remember, covalent bonds they share electrons. So when nonmetals bond, they pull on each other's electrons very hard because they both have high electronegativity. So everything you see over there on the right in green, those nonmetals, they have very high electronegativities and they pull hard on the electrons of other atoms. But since both also have high ionization energies, they also don't give up their electrons very easily. It takes a lot of energy to pull their electrons away from them. They don't easily give up the electrons. So if two strong guys are having a tug of war, nobody wins. Consequently, the two atoms share the electrons. So you have two atoms over there in the nonmetals that pull very hard on another atom's electrons, just like they do on the electrons of a metal. The difference is the metals have very low ionization energies, so it's very easy to take their electrons away from them. And so nonmetals will take the electrons away from metals, and they create ionic bonds. An anion, cation, they stick together. That's what we studied in the last lesson. Here now you have two fairly equally strong guys pulling on the electrons of the other. And since they're both strong and since they both hold on to their own electrons very well, neither one can win that tug of war. So they just decide to share the electrons, and that's a covalent bond. So the octet rule says that atoms are most energetically stable. We can say they're happy when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period, row, and below need 8 electrons to fill their valence orbital, their outer orbital. So oxygen has 6 electrons in its valence orbital. To be happy, oxygen will like to fill the 2 empty spaces. But how does it do this? Well, if a metal comes by, like lithium or calcium or something like that easily gives up its electrons, it can take those electrons away from lithium or calcium and fill those empty spaces that way. That would again be an ionic bond. But we're not dealing with lithium or calcium. We're dealing with other nonmetals. So the octet rule says that atoms are most energetically stable. They're happy when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period, row, and below need 8 electrons to fill their valence outer orbital. So hydrogen's valence orbital can hold 2 electrons. So hydrogen needs 1 electron to be happy to fill its valence orbital. And remember, hydrogen, even though it's on the upper left corner of the periodic table, is a nonmetal. So how does hydrogen do that? And note that even though hydrogen's first orbital can hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 valence electrons, so oxygen is happy. Oxygen likewise shares an electron to fill the valence orbital of each hydrogen, so the hydrogens are happy. So let's watch what happens here. There's a normal oxygen atom and 2 normal hydrogen atoms. So one of the hydrogens comes over, and now it shares its orbital and its electron with oxygen, and likewise oxygen shares that electron that it had with the hydrogen. They share electrons with each other. Similarly, on the right, same thing. The hydrogen comes over, it shares its electron with the oxygen shares its electron with the hydrogen. So those are the shared electrons there. So what you see is that oxygen now has 8 electrons in its valence orbital, its second orbital. So it's happy. It has a full octet, a full valence orbital. Similarly, hydrogen, its first orbital is filled. 2 electrons is all that can hold, so its first orbital is filled in each of the 2 hydrogens. So everybody has a full orbital. Now a full valence orbital. So you might say, well, wait a minute, you're counting those electrons that are in the purple there, you're counting those twice. You're counting them for oxygen. Let's say the one on the top. You're counting those 2 for oxygen. You're also counting them for the hydrogen on the top. And on the side, you're counting those 2 electrons for the oxygen, but you're also counting those for the hydrogen on the side. And that's true. You're effectively double counting those electrons. As long as they can both say that they have those electrons in their valence orbital, then that's perfectly fair, even though they're sharing the electrons. That's perfectly fair to say that they own those electrons. So oxygen owns 8 valence electrons, and each hydrogen owns 2 valence electrons, and everybody's happy. Because 2 hydrogens fill the valence orbital of oxygen and oxygen fills the valence orbital of 2 hydrogens, this combination creates H2O, or water. So these electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. Similarly, these electrons are double counted. They both belong to the hydrogen atom, and at the same time they both belong to the oxygen atom. The bonds created between nonmetals by atoms sharing electrons according to the octet rule are called covalent bonds. So think about that word. Co means together, like to cooperate, and valent means valence orbitals or valent electrons. So their valent electrons are shared. They work together. So again, remember, covalent bonds share. A diatomic molecule is a bond between 2 atoms of the same element. It actually can be between different elements. Diatomic actually means 2 atoms, but when we say it in this class, it means between 2 atoms of the same element. Diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens with 7 valence electrons, and here they are. So hydrogen is a diatomic molecule, so is nitrogen, oxygen, fluorine, and then you go down the halogens: chlorine, bromine, iodine. So you'll notice that those nonmetals over there on the right, they form the number 7. So that's how you can remember there's 7 of them, but there's only 6 elements there, so the 7th one is hydrogen over on the left side. So when you breathe oxygen, in other words, these 7 elements in gas form, when they're in gaseous form, meaning they're not attached to, they're not in a solution, in a liquid, or part of a solid. And naturally, these elements are gases. They float around, for example, in the atmosphere. When they appear naturally, they do form diatomic molecules. For example, the oxygen that we breathe is not oxygen atoms. It's O2 molecules. It's 2 oxygen atoms stuck together. Anytime you have hydrogen as a gas, it's not going to float around as hydrogen atoms. 2 of them, they're going to pair up, they're going to stick together, and you're going to have H2 molecules. And the same for all the others there that you see. So these elements always form a diatomic molecule when they are in gas form. So covalent bonds happen between 2 nonmetals. Nonmetals have high ionization energy and high electronegativity. They're both strong guys. Both nonmetals pull hard on the electrons of the other atom, but both do not give up their electrons easily. Since neither atom can win the tug of war, they decide to share their electrons in a way that they both fulfill the octet rule by having a full valence orbital. Sometimes this will lead to double and triple bonds, and we'll talk about that a little bit later. if one of the atoms has higher electronegativity, it will pull the electrons closer to it, creating a polar covalent bond. So think about that. If you have two different elements, oxygen and nitrogen, for example, nitric oxide, NO, oxygen has a slightly higher electronegativity than nitrogen. It's not strong enough to pull nitrogen's valence electron away from it, but it can pull it towards the oxygen. It tends to get pulled a little more towards the oxygen because oxygen is a strong guy who's just a little bit stronger than the other strong guy, nitrogen. So the electrons tend to get pulled a little closer to the oxygen. It's not an ionic bond. They don't totally get pulled over to oxygen, but they just kind of slightly get pulled on the oxygen side of the atom. And that's called a polar covalent bond. It means it has a positive side and a negative side. It's still an electrically neutral molecule, but one side tends to be a little bit more positive. That's the side that the electrons are pulled away from, and the other side tends to be a little more negative. That's the side that the electrons are pulled towards. Okay, so this is because oxygen is more electronegative than hydrogen, and what you would look at is your periodic table of electronegativities in your reference sheet section. So it pulls the electrons toward it. The water molecule below is polar. So this side of the molecule, that's the side in red, contains the nuclei of two hydrogen atoms, two protons. The red rectangle has a charge of +2. So if you just look at what's in that red rectangle, it's only two protons. That's all you see there. So that side of the molecule is more positive. This side of the molecule, the blue side, contains 8 protons and 10 electrons. So count them. The nucleus in the oxygen has 8 protons. And if you count all those electrons, all the electrons are in the blue section, then there's 10 of those. So the blue rectangle has a charge of 8 minus 10, or 2 minus charge. So the top, the red part, has a 2 plus charge, the bottom has a 2 minus charge. So the water molecule is electrically neutral. All in all, it has 10 protons and 10 electrons. 8 of the protons are in the oxygen, 2 are in each of the 2 total hydrogens, 2 in the hydrogens. Whereas it also has 10 electrons. You can see those, you can count those. So that means it's electrically neutral. It has the same number of protons as electrons. However, the electrons tend to be on one side of the molecule, that is the blue side, whereas the protons are a more positively charged side. So what does that do to the water molecule? It makes it kind of like a little magnet. So that positive side on the top will attract the negative side of other water molecules, or it could attract negative ions. For example, a fluorine ion, which is negatively charged. The bottom, which is a negative, can attract the positive side of other water molecules, or it could attract a positive cation such as sodium, Na. A polar molecule is an electrically neutral molecule that has a positive side and a negative side. This means that it acts like a magnet when the other polar molecules are nearby. And we should be a little more precise in the language there. Electricity and magnetism are related to each other very closely, but they're different. So you don't really want to call it's not a magnetic charge, it's an electrical charge. However, many of you have played with magnets in the past and seen how they stick together or they push apart from each other. And so I'm just trying to liken it to the way magnets work. Covalent bonds form molecules. These H2O water molecules, for example, are separate structures from all other water molecules. When water boils, the water molecules separate and move freely. They float up into the atmosphere, as you've seen when you see steam coming off boiling water. So you can think of them kind of like two cars. So think of molecules as cars that can move independently of one another. In other words, one car can move in one direction and the other car can move in the other direction. They're separate, independent structures that can move separately from each other. So let's compare that to ionic bonds, which we studied in the last lesson. Are they separate, independent structures? No. Ionic bonds form crystal lattice structures. Table salt, sodium chloride, has the formula NaCl. There is one sodium atom for each chlorine. The blue Cl atom is attracted to 4 sodium atoms, Na. It doesn't belong to any one sodium atom. So we mentioned that in the last lesson. So NaCl is not a molecule. It looks like a molecule, and sometimes it's even called the molecular formula, but it's not separate. You can't say that that chlorine in blue belongs to any one of those sodiums. It belongs to all of them. They fit together. The two analogies I use are like bricks in a wall or like apartments in an apartment building. You can tell one from the next, but they're not separate structures that can be moved about separately. So NaCl is called a formula unit or unit cell because it identifies that there is a one sodium for each chlorine. It's a one-to-one relationship. But you can't just go in and pull an NaCl out from a sodium chloride lattice structure. A formula unit is not a separate structure in the same way as a molecule. A formula unit defines the smallest basic unit of a crystal lattice structure, but it is not a separate structure. By repeating the formula unit, the entire crystal structure can be created. So there you see in the red box an Na and a Cl. That's the smallest structure of the crystal lattice structure of a sodium chloride crystal lattice. So it's not a separate structure that can be pulled away. However, what you can do is if you keep repeating that NaCl, 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 you can end up with a big block of salt. A formula unit is like an apartment in an apartment building. An apartment can be distinguished from other apartments, but it's not a separate structure that can move independently like a car. So just kind of keep that analogy in mind. What does happen to break salt apart? Well, you've seen it in real life. You put it in water and it dissolves, but it does not dissolve into NaCl molecules. It dissolves into chlorine ions, Cl-, and sodium ions, Na+. So the Cl's and the Na's break up. Once you put it in water, it's no longer sticking together, and each of those ions breaks apart into separate ions. Okay, Lewis dot structures. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So this is a diagram of a beryllium atom. If I asked you to draw beryllium, this is what it would look like in the end. And so what you do to get a Lewis dot structure, it's very simple. You write the atomic symbol, so for beryllium it's Be, and then you draw only the valence electrons around the symbol, and you draw them in exactly the same location. So this is why I had you draw the electrons when we did these diagrams the way that I did. So the first one is going to just go right there, and the second one's going to go right there, and that's how you draw the Lewis dot structure of beryllium. The point of Lewis dot structures is that only the valence electrons, they're the only ones that actually get involved in chemical bonding, so they're the only ones we really care about when we talk about chemical bonding. Even though it looks very simplistic, you can do some very sophisticated analysis on molecules simply with Lewis dot structures, and you're going to learn that in a later section, a later unit. Let's do another one. So Lewis dot structures show only valence electrons, since only these electrons are involved in chemical bonds. Let's see another one here. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So here's oxygen, the way you would diagram it. You've been asked to do that in one of your assignments. This is what it should look like. So you write the atomic symbol O, and then you go ahead and you place the electrons around it. Okay, and the key to the way you place the electrons is that there are two pairs of electrons, and then there's two electrons that are unpaired. Those are the ones that are going to want to form chemical bonds. We just saw that with hydrogen. That's how water molecules are made, from oxygen and two hydrogens joining up with those two unpaired electrons to form H2O. So that's the significance of unpaired electrons. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. So let's do phosphorus. See if you can do this one on your own. At least do it in your head. See if you can do this in your head. Okay, so we have a P for phosphorus, and then we're going to place only those outside electrons. Okay, and there it is. So phosphorus can bond in 3 different locations because it has 3 different unpaired electrons. The Lewis dot representation of a water molecule is shown below, so this is just a little repetition to emphasize it. All atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with a hydrogen if hydrogen shares its electron with oxygen. So there it is. Oxygen repeats this process with another hydrogen. So there it is. Both hydrogen atoms and the oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form molecules. They're independent structures that can move about freely and independently. A diatomic molecule is a bond between 2 atoms of the same element. Diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens with 7 valence electrons. So there's an empty space there in fluorine for 1 more electron. There's another empty space in the other fluorine for 1 more electron. Those are empty spaces. And they join up like that. Oops, sorry, that's a little quick. So they join up, you can count and see that both of them have 8 valence electrons. The 2 in the middle are credited to each of the different fluorines. So they get double counted. Okay, now we're ready to go. Okay, and each oxygen below has 6 valence electrons for a total of 12. So there you go, you see 2 oxygen atoms and each has 6 valence electrons. How can we create 2 octets from 12 electrons? So this is like a little puzzle. Before you go straight to the answer, you can pause the video. Just look at this. How could you form 2 octets? 1 for each of the oxygen atoms, so that they're both happy, both have a full valence orbital. But you only have 12 electrons to work with. 6 valence in the oxygen on the left and 6 valence electrons on the oxygen on the right. How can you get those to form 2 octets, 2 groups of 8? If you want to stop and think about it, do that now, and I'll give you the answer in just a second. Okay, so if you stopped and tried, great. If you didn't, well, let's find out what the answer is. That's how you do it. Each oxygen shares both of its unpaired electrons to form what is called a double bond. Notice that each oxygen atom has 8 electrons in its valence orbital because the electrons in yellow area are counted for both atoms. Anytime, whether it's a single bond, double bond, or there's even something called a triple bond, anytime they share electrons, you count those electrons towards the octet of each of the atoms involved. So those 4 electrons plus the 4 valence electrons in the oxygen on the left, you see them on the left side of that oxygen, there's 4 electrons over there, 2 pairs, plus the 4 in the yellow, that's a total of 8. And then the atom on the right, it has 4 valence electrons over on the right side, those 2 pairs, plus the 4 that are in the yellow as well, that's a total of 8. So each of those oxygens can claim to have an octet by sharing electrons. The Lewis dot structure diagram for the O2 molecule looks like this. In a covalent bond, electrons that bond 2 atoms are called bonding electrons. The electrons that do not bond 2 atoms are called non-bonding electrons or lone pair electrons. So that's some vocabulary that you should kind of commit to memory because we're going to use those terms quite a bit. A pair of bonding electrons can be represented by a line, but lines should not be used to represent lone pair electrons. So in other words, each pair of electrons is 1 line. 1 line represents 2 electrons, 2 bonding electrons. So down there you see 2 lines. That means there's 4 total bonding electrons in between those 2 oxygen. And then the electrons on the outside, in many cases, they're not even drawn. You don't even have to draw them. But if you do draw them, they're not drawn as lines ever. They are drawn as just simply individual electrons like that. So carbon dioxide, CO2, is what you exhale when you breathe. How does a carbon dioxide with two oxygens bond? How does it bond? That should be the question. How does it bond? There are a total of 16 valence electrons, so count them. Oxygen has 6, carbon has 4, and the other oxygen has 6. That's a total of 16 valence electrons between the 2 oxygen and 1 carbons. So how could they arrange themselves so that they bond in a way that the oxygen, the carbon, and the other oxygen all have octets? How could they do that? So stop and think about that for a second. You can even draw it out on a piece of paper. It's hard to do it entirely in your head. See if you can do it on a piece of paper. You have 16 electrons to work with, and you need 3 octets. Okay, here we go. And that's how it would do it. By creating double bonds between the carbon atom and each of the oxygen atoms, octets can be formed around each atom. So just convince yourself that each atom there has 8 electrons that belong to it, including those 8 in the middle around the carbon are being shared with the oxygens. Okay? All right, so convince yourself that those are octets. And convince yourself also that you didn't use more than 16 electrons because that's all you had to work with. So carbon forms double bonds with each oxygen. This provided octets for all 3 atoms. The Lewis dot structure of a carbon dioxide can be drawn with lines to represent a pair of bonding electrons, just like we saw before. Carbon dioxide, CO2, has a balanced charge. The 2 oxygen atoms pull on the electrons equally. So the charge is equally distributed. In other words, one of those oxygens is not going to pull on the electrons in the middle any harder than the other one. They're absolutely equally strong guys. So they're equally going to pull on the electrons in the middle. When electrons are not pulled to one side of the molecule is said to be nonpolar. So unlike a water molecule, which had a positive side and a negative side, carbon dioxide does not. The charge is evenly distributed throughout the molecule, and therefore it's said to be a nonpolar molecule. It doesn't have a positive side, it doesn't have a negative side. Now we're going to spend one slide talking about metallic bonds. In a metallic bond, electrons are attracted to the protons in the nucleus, but the electrons are not held closely. So we're talking about metals now, like copper and iron and aluminum, things like that. So the electrons are not held closely to any particular atom. So they jump around from one atom to the next when they are pushed. So copper, abbreviation Cu, has low ionization energy for its valence electrons. So it easily passes electrons from one copper atom to another. The yellow copper circles represent the nucleus of the copper atom and all the core electrons. So all you're seeing buzzing around there are valence electrons. The blue circles represent copper valence electrons, okay? And this is called the electron sea model because the electrons move like fish in a sea. Or else it's like I said earlier, it's like frogs jumping from one lily pad to another. But they don't call it the frog lily pad model. They call it the electron sea model because they're just swimming around like fish, and they're pretty free to move in between any of those copper atoms. They just freely jump between them like that. Now, if you put a negative pole on one end of those copper atoms and a positive pole on the other, the electrons will start to flow. They'll start to be pushed away from the negative pole and pulled towards the positive pole. So they'll have a flow in one direction, and that's what we call electricity, and we'll talk about that later on. Okay, so here's some characteristics that you should pretty much memorize about ionic and covalent bonds. So the unit. For an ionic bond, it's a formula unit. They form structures called crystal lattice structures. They're like bricks in a wall or apartments in an apartment building, but you can still identify one apartment from the next. And in the ionic compound, that would be a formula unit. It's the smallest unit that if you repeat it over and over again, you'll end up with that cube or with that crystal lattice. With covalent bonds, they form independent structures called molecules. So just think of them like two cars that can drive in different directions. When you boil water, you see steam coming up. Those are individual water molecules going in different directions. Some of them kind of go off to the right, some of them kind of go off to the left, and they can go in their own separate directions. They're actually individual separate structures called molecules in a covalent bond. Bond formation, ionic bonds pass electrons from one atom to another. The atom that receives it is called an anion. It's negatively charged. The one that passed the electron away is called a cation. It's positively charged. The positive and negative charges attract each other to form a bond from two ions that's called an ionic bond. With covalent bonds, they share electrons, as we just saw. The elements involved in an ionic bond are a metal, that's basically the center of the periodic table all the way to the left, and a nonmetal. That's the elements way over on the right, but not counting the noble gases. With the covalent bonds, they're both nonmetals. They're two strong guys. They have tug of war, but nobody can win, so they share their electrons. The physical state. Ionic compounds are solids. It's very difficult to melt an ionic compound. It can be done, but once you do, it's just like putting salt in water. It breaks apart. Those ionic bonds break apart. The covalent bonds can either be solid, liquid, or gas. The most obvious example is a water molecule is a covalent bond. Solid water is called ice. Liquid water we just call water, and gaseous water we call water vapor or steam. And again, the word gas does not mean like gasoline that people buy in a gas station. That's a totally different thing. It's the name of a substance that is used to power cars, but it's not what we're talking about here. Gas here means independent molecules that can break away from each other and usually oftentimes float up into the atmosphere. Melting point. So you can see that ionic bonds have a higher melting point. Covalent bonds have a lower melting point. One little simple experiment, it's almost like an elementary school experiment we do, is you take some salt and you put it in a little piece of tin foil, and you take some sugar and you put it in a little piece of tin foil, and salt and sugar look pretty much the same when you just look at them. But you put them over a flame and you'll see that the sugar will melt very quickly. It's a covalent bond, and it starts to turn brown and eventually black. The salt doesn't melt. You might hear some of it pop, but it doesn't melt under normal flame temperatures. Solubility in water, high. So ionic compounds like salt, you put salt in water, it's going to dissolve into sodium and chloride ions. Covalent bonds, it's very low. Now here's what you have to understand. If you put sugar in water, like you put it in iced tea or lemonade or something, and you stir it up, the sugar molecules will break apart from each other, one sugar molecule from another sugar molecule, but each of the molecules will not break apart. Sugar molecules are basically C6, I'll just give you one of them, C6H12O6. It won't break into separate carbons and hydrogens and oxygens. But one C6H12O6 will break away from another C6H12O6. So it dissolves in the sense that the molecules come apart from each other, but the molecules don't break up. So that's what it means when it says that they don't dissolve, covalent bonds don't dissolve in water very well. And conductivity. Because ions have positive and negative charges, like when you dissolve salt in water, and electricity is made of electrons which have negative charges, then ionic compounds, when they're dissolved, they have to be dissolved. They can't just be combined, put together. Like NaCl does not conduct electricity, but when you break it apart into Na plus and Cl minus so that it's charged, it does conduct electricity. That's what conductivity is. And covalent it does not conduct electricity well. Another simple little experiment we do is we dissolve salt in a beaker of water, and we dissolve sugar into another beaker of water, and we put two electrodes in, and you'll see that in the salt water you'll get electricity flowing through it. You can get a reading on a voltmeter, or even get a light bulb to light up. That's sometimes what we do. But through sugar water, you can't do it. It's not going to light up. It doesn't conduct electricity well. Okay? All right, so that takes care of Lesson 8, and it takes care of Unit 1. So we're done with this. So get this assignment in by early next week, whatever the due date says it is. And this is everything that's in this is going to be on the test. Everything is fair game, okay? So you will have open notes, so I think it's fair to make everything a part of this test. All right, so that's it, and we will see you all in class. You have a good day, have a good evening, and a good weekend if I don't see you till next week.